Philip Todd from Saltair Software. I'm going to talk about symbolic mechanics. There's a couple of browser apps that go with the talk that if you feel like it, you could download from that location. What I'm going to do is demonstrate our new software, mechanical expressions, which lets you create a visual model of a mechanical model and generates explicit mathematics from that, which you can then pull into Mathematica and manipulate. And I'm going to do this in a couple of relatively simple examples. Well, Archimedes is a hero of mine, not only because he created some incredibly elegant mathematics of limits and integrals, which were centuries, or actually millennia ahead of their time, but also because he invented machines for lobbing rocks at Romans. I'm not sure if a trebuchet was one of his machines, but trebuchet was used in the Middle Ages by the English for lobbing rocks at Scotsmen. And I encountered this on the TV, one of these programs where they get a posse of engineers to go and recreate some feat of antiquity. Usually the engineers mess around for a couple of weeks, and then the last day they bring in a backhoe. In this case, they were floundering around in a field in Perthshire trying to make a recreation of the trebuchet used by Edward I of England to reduce the fortifications of the town of Stirling. Edward I, by the way, had the sobriquet Malleus Scotorum, which translates to the hammer of the Scots. And so this was one of his prime modes of hammering. So a trebuchet, and as I was watching the TV, a very simple problem occurred to me, and I like simple problems, was this. If I have a big mass and a small mass, and I've got a beam of a certain length, and I want to make a trebuchet out of that, where is the best place to put the pivot? So starting with that, where do I put the pivot? Now, trebuchet is just a pendulum, and in fact, it's identical to the object that the people of a certain age recall as a metronome. For those of you that are too young, the way a metronome works, you would tune it by moving the lighter weight up and down, and that would change the frequency of the thing. So the problem, that's the problem I'm going to start with, and we'll see how to model it in mechanical expressions. Okay, that's an interesting screen. Okay, I'll start off with the coordinate system, which has kind of wandered. Drag it back there. Okay, so my trebuchet is going to look like that. It's just a beam of a certain length. I want my pivot point to be stationary, so I'll stick it at the origin here. And obviously I want to stick it on the beam. And I'd like to put a big mass here, and we'll call that capital M. That is big. And we'll put a small mass down here, and we'll call that small m. The length of the beam, I'm going to call A. So at this point, in a sense, we've put in all the givens in the problem. Now I want to put in the thing that I'm going to allow myself to vary. So I want to vary the length of this part of the beam. What I'm going to do is call that x times A. So I'll work with the proportion that I'm going to use. So now, the way mechanical expressions works, the constraints carry the forces. So I'm going to put a constraint in here on the angle of my beam. And if I want to know what the force, or rather torque, in that angle is caused by these masses that I've stuck in there, I just ask, give me give me the torque if it was stopped. There it is. Thinking about it, what I want to actually do, I don't really want to maximize the torque. I want to maximize the acceleration that, that I observe there. So that's the thing I would like to do. I can say, okay, free up that angle and give me the acceleration that it would that angle would experience. Of course, an angular acceleration. But here it is. And I see my x features in there. But it's a pretty simple thing. It's a rational quadratic. I've got every hope that I could be able to do something with that symbolically. So let's try. I'm going to copy as a Mathematica expression and go back into Mathematica, where I have a little scratch space here. So we stick that into Mathematica. And I just want to do the standard high school stuff. I'd like to differentiate it with respect to x. And then I'd like to solve that. With respect to x. Okay, I have my usual high school problem. I've got two solutions. I need to select one and grab it and stick it back into mechanical expressions. What I ought to be able to do is go up here and copy as MathML. I used to be able to do that, but I've gone and screwed up my settings on this particular computer, so what I'll do is go do it explicitly, which I can remember how to do down here. Here we'll do the explicit MathML generation and grab that. Humans should never really look at MathML. No, I didn't mean to do that. What did I do? Get down there. Ah, sorry about that. And I'm going to have a little, what I need to do is this, sorry. I need to make sure I get the whole thing appropriately. Okay, having done that, what I want to do is stick that in, the solution in for x. And there we go. Now notice, mechanical expression didn't actually move in any convincing way. We didn't see anything change when we stuck that solution in. Maybe that's a bit of a disappointment. What it did actually was it decided what numeric value for m and m would make sense given that distance. So it basically solved for m based on the geometry. If we want to see it move, let's put in a different value for capital M. Did I get that? It's not wanting to give it. What am I doing? And we can see it go to that. So we have the solution. What I think would interest Archimedes, if you saw it, was the actual form of that solution. There's a little bit of simplification that can happen. Let me just pull that into Mathematica to make it happen. I'm sure you can do it in your head, but I'll do it explicitly here. And simplify it. Oh, I've even got the handy-dandy simplify tool. Okay, so if Archimedes looked at that and he knew any algebra, he would see that this is actually a simple pendulum whose length is the ratio of the geometric mean to the arithmetic mean of the two masses. And of course, the way Archimedes would understand that, he would sit down in his Sandlot and draw something like this. Let's make that M. Let's make that one M. And let's just create a circle through the two. So take a midpoint there, draw a circle. Come out to here in a perpendicular fashion. And so now if we ask what the radius of that circle is, of course, it's the arithmetic mean. If we ask what that distance there is, it's the geometric mean. So that I'm sure it's how Archimedes would understand the solution to that problem, as you're creating a pendulum with a simple pendulum with that length, the length switch that ratio. Now, of course, famously, Archimedes was dispatched by a Roman soldier for drawing mathematical diagrams in his Sandlot and keeping the soldier waiting. Perhaps the most egregious example of the dangers of slow computation in history. Anyway, these modern engineers, when their trebuchet that they were assaulting a scale model of Stirling Castle didn't actually do the job particularly well, decided that they needed a bit of a redesign, and that having it stationary was not a good idea, that if they put wheels on, they could utilize the recoil. And so how would you deal with that in this system? Well, the constraints on C, one of the constraints is it's going to sit on the y-axis there, so we can get rid of that constraint. I'm actually also going to change this back to a times x, because that solution was definitely not for the mobile trebuchet. So now we can constrain the location of point C on the x-axis. So we're going to say, well, make yourself give yourself location t on the x-axis. So t is now a little variable that wanders it backwards and forward across the x-axis. Now you notice I didn't actually put velocities into that last situation. I happen to know that the velocity is immaterial in that particular. The angular velocity doesn't play a part. But here I'm not so sure. So I'm going to actually give a velocity of v to this parameter t, and I'll give a velocity of omega to that parameter there, to the angle. Now you'll notice the angle acceleration has not changed in any of this. The reason is that only the angle is free to move. So all the rest of that stuff is just locating the pivot point in a different place in the coordinate system. So it's immaterial to the actual mechanism. However, if I also allow t to accelerate, then I have changed the mechanics. And so this thing will recalculate and actually will involve omega, and then this one is even larger. Okay, well I could pull those into Mathematica and do some stuff with this. What I'd like to do is just show you one other mode of export that we have. I would just export a JavaScript, HTML5 JavaScript app. Let me do that for this. So just export this thing as an app. I'm going to turn that to false. A whole bunch of parameters I can change, and I won't. But we'll grab that. And so that creates an HTML file, which if I can locate it, probably called unnamed one. It has the trebuchet. It's got all the different parameters. I didn't need to put all those up there. I noticed that I've got my omega as 1. I don't want that. Omega 0. I want to start at 0. So now I can simulate it here, and you see that actually you get the feeling that there is a bit of an extra kick as it goes through the y-axis there. Let me just scale that out. And of course, if you think about it, the fact is allowing the pivot point to move allows that heavy weight to stay more or less vertical, which means you're not wasting any energy kind of pushing it off pushing it off to the side. So it seems reasonably logical. If you downloaded the apps, I have two. I have a stationary and a mobile one, kind of set up in the same fashion. You can actually observe what the we can see here. No, these are not the right things, so I won't show them. But you could be looking at the velocity. The apps that I have are looking at the velocity of that top bit. Okay, so that is the trebuchet. I do believe that the wheels were beneficial, although on the TV I can't remember. It was a bit inconclusive. Okay. So the second thing I'd like to look at is a little bit of chaos. A couple of years ago, we had a high school student with us in the summer. He was a junior, but had done calculus. He was going to be a senior the next year. He's now in Caltech, actually. What we thought we'd do is we'd give him. So he'd never heard of a differential equation. He'd got calculus, but hadn't reached the differential equations. And the thought was, well, what could a good high school student do with something that can generate the differential equations, mechanical expressions prototype that he was using, and something that can do stuff with the differential equations, Mathematica. Unfortunately, he didn't have Mathematica 9, which would have been really good for him. And so he ended up doing a very interesting project characterizing chaotic systems. Now, he wasn't doing anything new, but he was learning something about chaotic systems, and I certainly learned some stuff from what he was doing. So let me give you one of the simple models that he did. So we would take a pendulum, and stick a mass on the end of it. We need to constrain the length. Let's make that 1. And we'll constrain the angle. That's going to be theta. Now I'm also going to put another mass here on the x-axis. And we'll call that m as well. And I'm going to put a spring in between the two. And I get to set these parameters, but I'll make its natural length. Well, whatever. We'll leave it like that, and get rid of the damper, and get rid of the actuator. L has some value that it measured. It's actually going to take that as its initial value. So let's actually turn that down a bit. Put the spring under some sort of a tension. Okay, so those are the things that are given in the system. We're now going to constrain the location of that point. Now let me use D for this thing. And we've constrained this angle here. I'd like to give a velocity to this. Okay, so now we have a little model. What you can do, the way mechanical expressions works is it layers the different forms of mechanical analysis on top of each other. So at the first level, there's geometric analysis. We can ask what are the coordinates of that point. No surprise that that's what you get. You can ask for velocities. So that's the next level is a kinematic analysis based on the geometry. So I put a line in there if I want to know what's its angular velocity and acceleration. We can ask for that. So that's straightforwardly kinematics, which, as you can imagine, comes directly from the geometry. The next level is statics, where you've got some sort of forces in there, and you're asking for reactions. Now, as I said before, the reactions in mechanical expressions happen in the constraints. So you can ask for the reaction force in a constraint. So, for example, I can ask what is the reaction force in that length constraint. And so that, given the motion that's going on there, given the force that's in the spring, that would be the reaction force. Now actually, this is more than statics, this is actually kinetostatics, because the thing is moving. We're acquiring not just static force from the spring, but we're also acquiring dynamic force from the fact that we've got moving masses in the system. So I didn't show you statics, but on top of statics is this kinetostatics. And then on top of the kinetostatics is actual dynamics, where so kinetostatics is motion in, forces out. Dynamics is forces in, motion out. So you're basically solving F equals ma in the opposite direction. And with the dynamics, we're asking what is the acceleration in that angle. And let me ask the other question: what's the acceleration in this distance? Now at that point, we can. So what we have here are a couple of differential equations for theta and for d. So we can pull those into Mathematica. Down through all that stuff. So here I've pulled them into Mathematica, set them up a bit, stuck some numbers in for things that don't have numbers attached to them, and these are two accelerations. I can then define the whole thing as I have to define that the derivative of the velocity is acceleration, etc. And get my turn my second order differential equation into two second order differential equations into four first order differential equations, and then I can do my manipulate. Let me just make sure this stuff's all evaluated. Come on, should have just done it all once, right? There we go. So now for this whole chaos thing, the cool thing is this parametric ND solve value is a really great function, because you can attach that one parameter. In this case, I've attached the spring constant to my parameter. I can watch. Well, down there, if the spring constant is small enough, it's behaving reasonably. We're getting some sort of a periodic behavior, the occasional little jump. But once I add enough energy to the system, the thing goes completely chaotic. Of course, that's when I've got enough energy to push it over 12 o'clock, and by that time we've got complete chaos. As they say, chaos ensues. We can see that parametrically too here. We're looking at, in this case, we're looking at both parameters, theta and d, and so keep the energy small. And we've got sort of reasonable behavior, interesting behavior there, quite periodic, and then you go completely chaotic. Very, very nice little tool, this, for looking at that sort of stuff. Okay, so Mechanical Expressions is currently in beta and downloadable from the eponymous website. Thank you very much for your attention.